Hello everyone. In today's lecture we will discuss about normalization, why we use normalization, different forms of normalization and anomalies and different forms of anomalies. Basically, database normalization is used for controlling redundancy and reduce the complexity of the data and to ensure data dependencies. Suppose if your database objects are not in a structured or normalized way, it is difficult to update the database without facing the database loss. And without database normalization, the database system can be slow, inaccurate, and inefficient. Anomalies. Anomaly basically a data inconsistency or error. There are three types of anomalies: insertion, deletion, and updation. We'll understand by an example. There is a relation name employee, and these are the attribute of employee ID, name, department, and address. Next topic is update anomaly. If data items are scattered and are not linked to each other properly. For example, when we try to update one data item, having its copies scattered over several places, a few get updated properly while a few others are left with old values. Such instances leave the database in an inconsistent state. Come to this example. In this example, we have two rows for employee A, as he belongs to two departments of the company. Suppose we want to update the address of A, then we have to update the same in two rows, otherwise the data will become inconsistent. Insert anomaly. Suppose we try to insert data in a record that does not exist at all. In this example, suppose a new employee wants to join the company who is under training and currently not assigned to any department. Then we would not be able to insert the data into the table if employee department field does not allow null values. Delete anomaly. Suppose we tried to delete a record, but parts of it was left undeleted because of unawareness, or we can say the data also saved somewhere else. So in this example, we want to close the company department, so we have to delete all the information of an employee, otherwise delete anomaly occur. To overcome these anomalies, we need to normalize the data. Here are the most commonly used normal forms: first normal form, second normal form, third normal form, BCNF. Unnormalized relation. Basically, unnormalized relation contains non-atomic values. In this relation department, delocation contains multiple values. So this relation is unnormalized relation. 1NF. A relation schema is said to be 1NF if the values of each domain are atomic, means only one value is associated with each attribute. We will continue same example, relation department. So there are two main techniques to achieve 1NF for such a relation department. First method is we remove the attribute delocation, which contains multiple values, and place it in separate relation department location along with primary key d number. We decompose the relation into two relations. So in this relation, we decompose the department relation into two relation, department and department location. In next method, we expand the key so that there will be a separate tuple in the original department relation. But this method introduces lots of redundancy: a 3 times, 1 3 times, 4 3 times. Generally, we use decomposition method. We decompose the relation into two relation. 2NF, second normal form. Second normal form is based on the concept of full functional dependency. Full functional dependency means, suppose we have function dependency x tends to y. If we remove any attribute from x, means function dependency does not hold anymore. If functional dependency still holds, means this function dependency is a partial dependency. A relation schema R is in 2NF if every non-prime attribute A in R is fully function independent. Fully function independent means कि every attribute of a key, right? If primary key contains single attribute, test need not be applied. But if there are two attributes, we have to perform a test. Example. According to definition of 2NF, a relation schema R is in 2NF if every non-prime attribute in this relation, non-prime attributes are as ename, pname, p-location, is fully functionally dependent on the candidate key. In this relation, candidate key is security number and p number. But according to FD1, ours is fully functionally dependent on security number and P number. But ename is partial because ename dependent on only security number. So this relation is not in second NF. Another example. Plots relation. Suppose there are two candidate keys, PID and name and plot. PID is single attribute, so single primary key, but there are two attributes, name and plot. So we'll check. FD1 is okay because PID is single attribute, so every attribute dependent on primary key single attribute. In FD2, all the attribute dependent on all the primary keys, but in FD3, text rate is partially dependent on name. So this relation is not in second NF. I told you in the previous slide that plots relation is not in second normal form because of function dependency in which text rate is partially dependent on candidate key. So we decompose the plots relation into plots 1 and plots 2. Then we remove the attribute text rate. There are two relations, plots 1 and plots 2. In plots 2, text rate is dependent on name. 3NF. 3NF is based on the concept of transitive dependency, means if there is a set of attribute that is neither a candidate key not a subset of any key of R and both X tends to Z and Z tends to Y hold. There are two important points for 3NF. A relation schema R is in 3NF if it satisfies 2NF and no non-prime attribute of R is transitively dependent on the primary key. It's very important. And the second one is a relation schema R is in 3NF if whenever a non-trivial functional dependency. Non-trivial functional dependency is basically if a functional dependency X tends to Y holds where Y is not subset of X, then it is called non-trivial functional dependency. So in this relation, non-trivial functional dependency X tends to A holds in R. Either A X is a super key of R and B A is a prime attribute of R. We'll understand by an example. This is relation plots 1. We'll check if this relation is in 3NF or not. So first we will check first condition. According to first condition, no non-prime attribute of R is transitively dependent on the primary key. No non-prime attribute is price is transitively dependent on both the keys PID, name and plot. So according to first condition, this relation is not in 3NF. Now we'll check second condition. According to second condition, either X is a super key. According to FD4, area tends to price. So area is not a super key. Or A is a prime attribute. A means price. Price is a prime attribute. No, price is not a prime attribute. So this relation is not in 3NF. We decompose the relation plots 1 into plots 1A and plots 1B. We construct plots 1A by removing the attribute price and placing it with area into another relation plots 1B. Now both plots 1A and plots 1B are in 3NF. This is general definition of 3NF. Means first it is fully functionally dependent, means relation should be in 2NF. Then it is non-transitively dependent on every key of R. If we have unnormalized relation, so for 1NF we have to remove repeating groups. For 2NF we have to remove partial dependencies because 2NF is based on the concept of full functional dependency. For 3NF we have to remove transitive dependency, right? BCNF. A relation schema R is in BCNF if whenever a trivial functional dependency if functional dependency x tends to y holds where y is subset of x, then it is called trivial functional dependency. So trivial functional dependency x tends to a holds in R, then x is a super key of R. The basic difference between the definition of BCNF and 3NF is that condition A is prime attribute of R is absent from BCNF. We'll understand by an example. Now we will check this relation, if this relation is in 3NF or not. Look, first we check FD1 in which PID, name and plot, these are candidate keys, in which name, plot, area dependent on primary key. So this is okay. Now FD2, which is also okay because ID and area dependent on name and plot. But in FD5, name dependent on area, where area is not a super key of plots 1A. So this relation is not in BCNF. But this relation is in 3NF because a name is a prime attribute. We decompose the relation plots 1A into plots 1AX and plots 1AY. We will check another example. Most relation schemas that are in 3NF are also in BCNF. Come to this example, A, B, C. A and B are prime attributes where C dependent on A and B, okay, and B dependent on C. So according to FD2, C is not a super key. So this relation is not in BCNF, but this relation is 3NF because B is a prime attribute.